Our next call this morning is Daniel Litt on non-abelian phase one.
All right, can everyone hear me? This working? All right. I'm really happy to be here. Nice to get away from the whole other so I want to tell you about an elementary problem with linear algebra that's often in couple places recently, and how you can say something about it using the hot theory and many of the things we've discussed over this week. Everything I'm going to say is joint work with Aaron Lansman, and if you want to know more, you can look at the paper on the archive, which went up in May 2022. If I have time, I might say something about more recent work as well at the end. All right, so let me start with some motivation. So suppose you have a family of varieties over some base. Maybe I'll assume it's smooth and proper. And in this case, there's a kind of linearization of the geometry of this map. Namely, there's a representation of the fundamental group of the base on the cohomology of the fiber. So that's the monodromy representation. And this is a sort of precursor of what I want to tell you about today. I think there's some kind of slogan in algebraic geometry that if you have a representation like this, the image of this representation, so the monodromy group, should be as big as possible. So any constraint that's not forced to satisfy by the geometry, it should not satisfy it. In other words, this representation should reflect well the geometry of the situation. So let me give you maybe the most basic example. So suppose I have a universal curve CG over the moduli space of genus G curves, MG. Well, in order to talk about pi1 of the base, I need to pick a base point. So a base point and a point in MG is a curve, which we'll call C. And in this situation, we get a representation of pi1 of MG on the cohomology of that curve. And I told you that, well, this is a monodromy representation, so I told you it should have big image. And well, what does that mean? It means it satisfies exactly two constraints. So in this case, it preserves the integral structure on the cohomology, so it lends an arithmetic group, and it preserves the intersection pairing on the cohomology, the cut product. So the map factors through the symplectic group, exactly the group of integral matrices, preserving that intersection pair, and in fact, that map is projective. And that's not a totally trivial theorem, but not very hard. So let me generalize this situation very slightly. First, so I don't want to just consider smooth proper morphisms. So in particular, most of the talk I'll be talking about the universal puncture curve of MGN. So this is a family of curves of genus G minus n sections and disjoint sections. And I'm going to fix a curve C0, which is a point of MGN. So think of that as a punctured curve. And in this case, we get a representation of pi1 of MGN on the cohomology of that punctured curve. The image is a little more complicated. In particular, that representation is not semi-simple, but nonetheless, it's something we can understand. But I want to discuss what's the substantial generalization of this representation. So a kind of non-abelian analog. So this is the non-abelian version. We just replace that H1 there with pi1. Okay, so pi1 of the mapping class group acts via outer orthogonalisms on pi1 of the moduli space of curves acts via outer orthogonalisms on pi1 of the fiber. Okay, and I'll discuss this in a number of ways, but on the next couple of slides. But the easiest way to see this is that there's a short exact sequence of fundamental groups. Pi1 of fiber goes to pi1 of CGN goes to pi1 of MGN, and that induces an outer action. So in other words, if you choose any element of pi1 of MGN, you can lift it to pi1 of total space, and then it'll act on the fiber by conjugation. And that action is well defined up to inner elements.
I thought that in MGN, the endpoints are ordered.
Yeah, so that is
not exactly true.
So it's still true that there's an action, but you're right that the action extends to the bigger group, the mapping class group.
It's a smaller group.
Yeah, so this is a fine.
The difference between color grades and non-color grades.
That's right. But nonetheless, everything on the slide. So this one action.
Of course, you never say this is big.
Yeah, that's right. Yeah. So this map is not projective. It's actually, if n is 0, this map is in with finite index. Oh, maybe it's what you were saying. But we completely understand the meaning of this map. It's a very explicit thing. both groups, if you'd like, have very nice presentations by generative relations, and this is a well understood object. So when I say that this map is a big image, I'm not just talking about the literal, I'm talking about some kind of invariants of it, which are a little more subtle. Okay, so here I arguably slightly lied, so let me tell you a little bit about this group, pi1 of MGN. So I'm going to define it as mod GN. I think there's some disagreement in the literature about this, so maybe your definition would be finite index. But let me just make a definition. So it's pi0 of the group of orientation preserving homeomorphisms of a surface of genus G with n mark points, but I want the only is to fix the markers. This is what we're saying. Okay, so there's an explicit topological description of this group. You can also write it down via generative installations if you'd like. And I think we saw some of those generators in Manuel's talk. So those were the Dane twists that Manuel discussed. So as I said on the previous slide, this group has an outer action on pi1 of a curve. So it maps to the outer automorphisms of pi1 of a curve. And what that gives us is an invariant, which what we saw in Donner's talk, namely that mod GN acts on the space of r-dimensional representations of pi1 of a surface group, pi1 of sigma GN, up to conjugacy. So I want to study this action. So the big question I want to talk about are some variants of the following question. So does this action have big N? And there's a number of ways to formulate this precisely. I think much work on this has been done by Goldman, Pickrell, and Shaw. So they formulated this big image question as saying that the action is organic with respect to some natural measure on the character variety of the space of representations. And they proved that in a number of settings, maybe if this general linear group is replaced by a unitary group. And then variants of this question have been studied also by Kasserkopf, Pendev, and Simpson in the case where you have a Lefschetz pencil. And they proved some kind of big image statements in that setting too. So are there any questions about this action? Because this is what we'll be studying the rest of the talk. Okay, so the main question I want to discuss, and I'll motivate that in a second, is I want to talk about what are the finite orbits. So I think the most naive possible formulation of this big image question is, well, are there very few finite orbits? Right, so can you classify them, for example? What are the finite orbits of this action? And this question has come up in a number of places recently. Before I tell you where, let me give you some examples of this action. Okay, so the simplest example we've actually already seen. So take the case where we're looking at rank 1 representations and n is 0. So here we're looking at representations into C star. So we have an action of the mapping class group, pi1 of mg, on C star to the 2g, that's the space of one-dimensional representations. And that's just the same as the cohomology of the surface with C star coefficients. So that's the same as the integral cohomology tensor C star, if you'd like. So we know exactly what the action is. It factors surjectively through SP2G. Okay. So it's exactly the same action we saw before. Maybe just to show you it's not always this simple, let me give you a different example. So suppose G is 0. So we're in the genus 0 case. We're looking at P1 minus a bunch of points. Well, then what is the space of representations? It's just n tuples of matrices whose product is 1 up to conjugacy. So this is a local system or on sigma 0n, or representation of pi1 of sigma 0n up to conjugacy. So local system on P1 minus some points. And what's the mapping class group action? Well, if I'm going to describe a slightly larger group acting on it, so the group where you don't fix the points, and it's generated by the following automorphisms of this set. Given an n tuple of matrices, you are allowed to swap the I matrix and the I plus first matrix at the cost of conjugating the I matrix by the I plus first matrix. And if you stare at this formula for a couple seconds, you'll see it preserves the property of the matrices multiplied by 1. So this is an action of the braid group on the character variety of a genus 0 surface minus n points. And the question I want to talk about is, what are the finite orbits? Okay, are there any questions about this? Okay, so there have been a number of conjectures recently made about this action, and so I want to motivate them by going back to this very simple example. So we have the mapping class group acting on C star to the 2G, and we saw earlier that that action factors through SP2G. So we completely understand this, and so in particular, we know what the finite orbits are. So the first observation is that, well, the finite orbits are exactly the torsion points since these are the two G equals. So that's like a little exercise that you get bored during the talk, you can kind of look at yourself. It's just a fact about sp2g acting on this space. Well, since we know exactly what the finite orbits are, it's easy to say the second thing that we observe, which is that the finite orbits are Zariski X. So the roots of unity are Zariski X and C star, and so n tuples of them, 2G tuples of them are dense in C star to the 2G. Okay, and maybe in the last, I guess, 10 or 15 years, people have. Of course.
If finite orbits are torsion and torsion points are. You mean not the union of all the
The union of all the Zariski X, yeah. So part 2 here means that the union of all finite orbits is Zariski X. Exactly right. Okay, so in the last 15 or so years, people have conjectured that both of these things generalize beyond this case. So generalize to higher genus, arbitrary genus in N, and arbitrary rank in particular. So here's the action we're studying, and here are two conjectures that have been made about it in the last 15 or so years. So first of all, there's a conjecture. I think that this was maybe first asked as a question by Kissin around 2010. So he asked if, well, there's some obvious finite orbits. Namely, if you have a representation of finite image, then the measuring question can't make it around. So that's a generalization before. So Kissin asked, without this G big condition, and then Wang corrected it to this G big condition, if the finite orbits are exactly the representations of finite image. So this is false if G is not being compared to the right. So, and I'll give some examples later. So I think Kissin was motivated by some potential applications from arithmetic, so from the curvature conjecture, and Wang was motivated by the work of Bourgain and with Sarnak on strong approximation comparative. So both of the people who asked this question and this conjecture were motivated by arithmetic. Okay, so this is one of the conjectures I want to talk about. So maybe I mentioned earlier, you really need this hypothesis that G is big, and I'll give you lots of interesting examples of finite orbits later in the talk. When I say naive here, I don't mean this in a negative way. I think this is the most basic question you could ask about if this action has big image. So it's asking, well, are there any non-obvious finite orbits? I think that's a virtuous question. So here, there's a conjecture which is very inspirational, I think, by Eno Kurtz and Guder Wang. So Wang is in this room. And I'm only stating a consequence of their conjecture here, so their conjecture is something much stronger, which I'll say a word about in a second. But whatever their conjecture is, it implies that the union of all the finite orbits is Zariski X. So what they actually conjecture is that if you have any, let's say, smooth complex variety whatsoever, the representations of its fundamental local systems on it, which are of geometric origin, are Zariski X. And that implies this if you apply their conjecture to, let's say, a very general curve. It's a little exercise. Okay, but I'll just talk about this conjecture. Great. So those of you in the room who are particularly sharp-eyed may have noticed that these conjectures contradict each other. So if R is bigger than 1, it's not so hard to show that representations which are finite image are not Zariski X in the character in the space ball. Okay, so which one's true? Okay, so these are the conjectures. Are there any questions about the conjectures?
The first conjecture is paternity. The second, that's a consequence of this.
Yeah, I can tell you what the precise conjecture of any person but it is much stronger. Yeah, so in particular, resolving this question in the negative results their conjecture, and that's what we do. So jointly with Aaron Heinzman, we showed that if G is big compared to the rank, if you have a representation with finite orbit and finite class group, then it is finite. So in particular, this resolves Kissin and Wang's conjecture positively, and it resolves Eno Kurtz and Guder Wang's conjecture negatively. Okay. Yeah. Nonetheless, I really do think some version of this Eno Kurtz Guder Wang conjecture is true, and I really think there's some beautiful ways one could help to salvage this and really get some mileage out of it. Okay, and so the proof is going to rely on some non-Euclidean Hodge theory. So in particular, the work of Takuro Mochizuki and Carlos Simpson. and also a little bit of input from the language program, so the work of Daniel Groy on logical visual systems that we already saw mentioned in Bottom's talk. All right, how am I doing? Great. Are there any questions about the statement here? So let me just reiterate. So maybe if we're stressing, like really, this is a statement you can in linear algebra.
Yes. There are plenty of these representations, conjugacy classes, finite.
Yeah, so if R is big, so if you're outside of this regime, there's lots and lots of examples. I'll give one. Yeah, so it's really this hypothesis, probably this inequality is not sure, but some hypothesis on the genus and rank. Yeah, but no.
And doesn't play a role.
Yeah, that's right. It's kind of interesting. So okay, n plays a role in the group. When n is positive, it's a much harder theorem, basically because it requires some mixed theory. But yeah, it doesn't play a role in the statement. My guess is that when n is big, actually you get a stronger result. And I'll maybe we can prove that in some cases. So this theorem says nothing in genus zero in particular. And genus zero is sort of the most classically studied case, so I think that's kind of a shame. But if I have time at the end, we have some new results in genus zero where when n gets big, and so really n getting bigger only helps you. All right. So what I want to say is this is like so the mapping class group is some explicit group you can present by generative simulations. It's outer action on pi1 you can write down explicitly, and so you can write down explicitly the action on like the matrices defining the representation. So this is like a question you could pose to an undergrad, and I would be very interested in finding an undergrad style group. Like I don't think it's kind of fair that such an elementary statement requires these kinds of techniques. So I think that would be very interesting if anyone can say something about it. Okay, so I want to, before telling you about the group, I want to tell you something about the history of this question. So I kind of didn't know this when I first found out about Kissin's conjecture, which is sort of when I started thinking about this. But actually, in some sense, this question has been studied since the beginning of the 20th century. So I think it's maybe fun to learn about. And actually, that the perspective that people took in 1905 or whatever is essentially the perspective we need to take for the proof. Okay, so here's where the story starts. So this is a nonlinear ODE of second order, the Penlove-Six equation. And I claim it's related to the case of this problem when the genus is zero, we have 4 marked points, and you're looking at rank 2 representations of the fundamental group. So this is the Penlove-Six equation, which was written down not by Penlove, but by Richard Fuchs in 1905, and he was actually thinking about this precise problem. So the observation, and I'll explain where this comes from, is that algebraic solutions to this Penlove-Six equation correspond in some suitable sense to finite orbits of the action of pi1 of m04 on 2-dimensional representations of p1 minus pi1 of p1 minus 4. Of course.
I know lots of Fuchs, the Fuchs and
Yeah, this was his thought.
Then
I think this was his thought. Yeah. There's 2 Fuchs. Okay, so I'm not a mathematical historian, so I'm just remembering from Wikipedia. Yeah. Okay, so where does this come from? So I'll tell you that soon, but I want to tell you something about the history of the study of algebraic solutions to Penlove-Six, or equivalently finite orbits of the action of, well, mod 04 is just the free group on 2 generators is pi1 of p1 minus 3 points. That's m04, and its action on this space of representations, which is essentially a family of cubics. So it's a very concrete question. So we're interested in classifying these finite orbits, and I as I said, I'm not a mathematical historian, so please forgive me if I say anything not quite right. I'm trying to explain some history that I learned from Philip Bolch, but any errors are mine, not his. So according to Philip, the classification in some sense begins with Schwartz and Poincaré. We're working on this before the Penlove-Six equation was even written down. But Schwartz, for example, wrote down the classification of hypergeometric equations with finite monitoring. So that's the case of representations of pi1 of sigma 03 into SL2C finite image. Okay, and then this, in 1905, people wrote down the Penrose-Six equation, and I think there was some interest in finding algebraic solutions in particular, because most solutions are very transcendental. They're called Penrose transcendents. But then I think the interest in this was really revived by Hitchin in 1995 when he discovered some new algebraic solutions to Penrose-Six, and then the study took off with work of Andreev and Bolch and Kitaev and Doran, and who all found beautiful examples of algebraic solutions, and then Dubrov and Motsako, who classified them with some assumptions, and then finally the classification was completed in 2014. So I guess 110 years after the Penrose-Six was written down, and with a computer-aided proof by Litt and Kiki. So the class, it's actually kind of cool. It turned out that Litt and Kiki discovered that all the algebraic solutions had already been discovered by the time they got to the problem, and then their work was showing that the list was actually complete, which again required the use of a computer. And the nature of their classification is that there are 4 continuous infinite families of solutions, 1 infinite discrete family, which is really beautiful, and that's my favorite one, and then 45 exceptional solutions. And so there were some questions: are there examples of these representations of finite mapping class group orbit with infinite image? And already in this case, there's many examples. So in both the continuous and infinite discrete families, there's cases with infinite image, and also in the exceptional solutions. So for example, there's a representation of pi1 sigma 04 into SL2C with finite orbit, where the image is the 237 triangle group. That's an infinite interesting group inside of SL2C. All right. So are there any questions about this classification? This is just history.
Discovered Hitchin.
I'm sorry?
Which ones were discovered by Hitchin?
So the Hitchin, yeah, so it's sort of funny. So when I say this family is this FSM equivalence relation, but so the ones he discovered were in this infinite discrete family. And they come, I can even tell you what they are. So if you take P1 minus 4 points, there's an elliptic curve branched over this, over the 4 points, and if you take minus the 2 portion. If you take a character on this and push it forward, so if it's finite order, that gives you a solution. It gives you a solution, and if you change the order of the character, the size of the order becomes unbounded.
So you take the curve of genus 2.
Sorry, so this is the curve of genus 1, and branched over these 4 points. You take a range 1 local system on this with finite order, and you push it forward.
You take
a range 1 local system, and you push it forward. Okay, so this is one example, but then somehow there's actually a really beautiful thing you can do, which is if you have a solution, you can create more of them via Katz's middle convolution operator. We'll hear about more. And so this produces new examples with infinite monotromy. So where the monotromy is given by 1, 1, 0, 1 at 4 points. So sorry, 1, 1, 0, 1 at 3 points, and then minus 1, 1, 0, minus 1 at 4. So already in this infinite discrete family, there's examples with finite monotromy and examples with infinite monotromy. And I think this points to kind of the difficulty of the classification. So if you look at this infinite discrete family, the orbits under M0 under mod 04 are unbounded. So this tells you, even if you want to search with a computer, you have to be a little bit clever. It's not a finite classification. Okay. Let me tell you about a bit of a generalization of this. So suppose the genus is 0, and now we're looking at n mark points, not just 4 mark points, and rank arbitrary. So we saw an algebraic formulation of this question earlier. This is the gradient action on n-peoples matrices. So how was this studied historically? Well, to this data, if you choose a complex structure on P1 minus n points, and maybe I'll choose so that infinity is not one of the n points, you can get a logarithmic flat vector bundle on your genus 0 surface, genus 0 curve rather. Maybe I'll, for simplicity, assume E is a trivial is a vector bundle, and then the connection will have this form. And I'm going to assume also, just for simplicity, that the sum of the AIs is 0, the sum of these residue matrices. So that is the effect of forcing monotromic infinity feature. Well, then what can you do? If you have this data, you can move the points around. You can change the complex structure on P1 that's deforming the lambda I. And you can ask, well, how do I change the AI, the residue matrices, to keep the monodromy fixed? And Schlesinger told us the answer in 1912. So he showed that if you want to deform the lambda I while fixing the monodromy, the AIs, these residue matrices, will satisfy the so-called Schlesinger equations, this sort of complicated system of nonlinear ODE. The case when R is 2 and N is 4 reduces the Molière 6 equation we saw earlier. And well, what does it mean if your representation has finite orbit on the Demanding Cauchy? It means exactly that the solution to this differential equation is finitely branching. So in other words, it's an algebraic solution to this differential equation. And what that tells us is that the algebraic solutions to this differential equation are up to some mild equivalence relation, the finite orbits of mod 0 n, the mapping class group of I1 of M0 n on the space of r-dimensional representations of pi1 of P1, for example. Okay. And well, you could ask to classify these, and there's lots of examples known. I'll tell you some of them soon, but a classification seems really, I think. This is well, I'll make a conjecture and talk about what one might look like, but I think this sort of conjecture I'll make, you'll see, would not really have been accessible to Schlesinger or Candelet, and I think it's questionable whether it's accessible to us. Okay, so let me give you some examples of finite orbits or equivalently solutions to these ODEs. Maybe I'll just mention there's you can generalize these ODEs to Venus. I think they go by the name non-Abelian Gaussian connection in that case. It's a little hard to write down explicit formulas. Okay, so what are some finite orbits? So I think the first example is, well, in genus 0, we can look at rigid local systems. So these are local systems on P1 minus a bunch of points, which are determined by the local monodromies at this point. So equivalently, if you look at the character variety, parametrizing representations with fixed local monodromy, they correspond to isolated points. So these were classified by Katz in a beautiful book, and that's the origin of this middle convolution operator I mentioned earlier. It doesn't really matter what it is, it's a little bit complicated. You could ask, well, why doesn't this work in higher genus? And of course, a rigid local system would always have finite orbit under the mapping class group. Why is that? Because the mapping class group commutes the zero-dimensional components of this variety. Well, and the problem is that there are no rigid local systems in higher genus. So it's yeah. So this only gives examples in genus 0. Okay, there's also these trivial examples. If you have a representation with finite image, it has finite orbit. Okay, so what are the non-trivial examples? So the non-trivial examples, the main source of them is that if you have any local system on CGN, the universal curve of genus G then mark points, then it automatically has finite orbit. But that's just a little exercise. It's fun to work out. Okay, so where are we going to find interesting local systems on the universal curve? Well, again, in genus 0, Kostov made the observation that this middle convolution operator that Katz defined makes sense even in the non-rigid case. And I learned this one, paper Carlos. So you can take any representation which you know has finite orbit under the mapping class group. So, for example, a representation of finite image, and apply this middle convolution operator. Whatever middle convolution is, it's very complicated. So it sends things with finite image to things that don't necessarily have finite image. So you can produce interesting examples this way. There's variants of this construction in higher genus, which probably won't say anything about. Okay, there's another source of local systems on the universal curve for MGN, which is TQ of T. For example, you can look at conformal blocks. I won't say anything else about that. I'm sorry? A topological quantum field theory. Yeah, it would take me, I mean, I don't know that much about it, but what I do know would take up the rest of the time. Okay, but let me give you kind of an algebraic geometric construction. It's very classical. So, well, how do you make a local system on a variety? You find a family of smooth proper varieties over it. Take their homology. Right. So how do you make a family of smooth proper varieties over the universal curve? Well, you use direct function. So what is that? Well, you can view the universal curve as a modular space. Modular space of colors branched over a point. So, okay, what is the point of the universal curve? It's a curve with a marked point, let's say away from your other end. And so you write down a family X, where the divisor over a marked curve is a cover of that curve around the divisor. Now, if you want to make a local system on the universal curve, you just take the homology of that. And okay, well, to check that, you have to check that this is an interesting thing. This is an interesting local system, but that's not so hard. Maybe I'll just mention understanding the monitoring of this local system is a very interesting question, and it's not something people understand well. So I'll probably briefly mention there's a conjecture of Putnam and Wheeland about monitoring this local system, which maybe I'll mention at the end of it. So already there's many interesting questions about just this example. Okay, so the moral, I think maybe this, I hope you'll forgive this philosophical comment, is like there are lots of interesting, it's a little bit hard to find orbits, but every time you do, they're related to zero. So I think, especially, I really love the classification of rigid local systems, and I think the classification of these finite orbits is a plausible generalization of that story to higher genus, or at least a plausible generalization of that question to higher genus. Okay, so let me make some conjectures about the picture before I tell you about the proof of the main theorem. Maybe I should pause. Are there any questions about any of these examples? So here's a picture. So what I've done here is I've graphed. Of course.
You say any local system.
Yes.
Can you give examples?
Yeah.
Because so that's a theorem that for all local systems on the curve.
Yeah.
Because it looks like remind me of this Franchetta conjecture, which was proven that the only rational determined like boundary moduli space. Is it related?
So I don't know a direct relationship. I think it's a moral relationship. So I'll comment on this at the end of the talk, but yeah, so right. So the statement is that if you have any local system on the universal curve, you can just restrict it to a fiber of the universe. Yeah. And that will give you a representation of G minus n points. And in fact, that representation will not only define an orbit, it will actually be fixed by that. That's not much of a restriction. If you have anything defined orbit, you can just take the direct sum over the orbit. So classifying fixed points in finite orbits is kind of the same thing. Yeah, so you could ask, well, what are the local systems on PGN? Like maybe you can classify them, and I'll make a conjecture about that. Maybe in 2 slides or so. Any other questions about this? Okay, so here's a picture. So I've graphed on the x-axis genus and on the y-axis rank. So what I would like to talk about is representations of pi1 of a genus G curve of rank R with finite orbit under the mapping cluster, under pi1 of MGN. And I haven't put n in the picture because it doesn't enter into the surface. But you could put n in the picture, and then it would be 3-dimensional, and then I wouldn't be able to draw. Okay, so the main theorem of the talk I'm giving now is the red region. So it says that in the region where the rank is small, so R is less than the square root of the genus plus 1, any representation with finite orbit under the mapping cluster is finite image. So I'll spend the last third or so of the talk proving that. All right, so I didn't tell you, but I know how to make a lot of examples of rank polynomial in G where the representation is virtually solvable. Okay, so this is not a theorem, this is a statement that all the examples I know in this range where the rank is polynomial in G's have virtually solvable image. And if you're interested, I can tell you how to make some examples, but it's a little bit involved. And then finally, in this regime where the rank is exponential in the genus, there's a huge slew of examples. Include all the examples in this previous slide. So in every example I've checked, where you have a family of representations of rank R and genus G, the rank, and they're sort of interesting thing. Let's say they're semi-simple with infinite image. The rank is growing exponentially in the genus. Okay, so in this regime, this sort of blue regime, there's a huge collection of semi-simple infinite image representations. So okay, one conjecture you might make is that the picture looks like this. So in this main theorem, we show that R is small, our representation has finite orbit, then it has finite image. You could ask if you additionally assume the representation is semi-simple, can you improve this back? I think that's very plausible. But let me make a much stronger conjecture, and I view this conjecture as some analog of Margulis' superrigidity for the mapping class group. So the conjecture is that if G is at least 3, all irreducible local systems on MGN are root. So in particular, MGN is CGN plus 1, n minus 1, rather. So this makes a conjecture about these representations of finite orbit. And I told you that if you have a local system on the universal curve, then it's finite orbit. There's actually a partial context for that. So this would really be, in some sense, this would be a statement about all representations of finite orbit. So let me expand on that a little bit and expand on the analogy to superrigidity. So what's the main consequence of this? So the main consequence is that if you believe Carlos's conjecture that rigid local systems are of geometric origin, well, this would imply that any irreducible local system on the moduli space of curves, at least in large genus, is of geometric origin. So I would say that there's a geometric explanation for all these finite orbits. I can make that precise if you like. Yeah. So of course that's not really a classification. You can't break down a list, but it would be if this is true, it would be a structural property for these finite orbits. Maybe let me just say a word about the motivation. So there's some, if you talk to a low-dimensional topologists, they'll tell you there's some analogy between the mapping class group I1 MGN and lattices in simple regions. And well, such lattices in large rank, so for example, SL3Z have the property that all their complex representations are rigid. But in fact, there's a stronger statement here, which is so let's suppose we apply that statement to SP2G, the fundamentals of the multiplexes of abelian varieties. Well, what it tells us is that actually every local system on that multiply space is of geometric origin. It kind of comes from the universal abelian variety. So this would be an analog of that for moduli space of curves. Okay. No, maybe I'll just make one more remark. I mean, a big part of the motivation is that the proof of the main theorem will go to proving some kind of rigidity. So not this very strong statement, but some of a rigidity statement.
Because Ivanov's conjecture.
Yeah.
Really,
Yeah, so that's part of the motivation. Yeah, so I would even guess infinite doesn't. Yeah, in fact, Ivanov's conjecture even follows from if Ivanov's conjecture is false, you can make it. Yeah, even if it's well, genuinely not rigid, not infinitesimal rigid levels. Yeah, and then of course part of the main theorem will go towards proving something that something a bit weaker than something. So part of the way I got into this is Are there any other questions about this? Okay. So let me tell you something about the idea of the proof of the main theorem. So let me just maybe remind you what the main theorem says. So it's a pure statement in linear algebra. If I have a representation of this group, well, n is positive, it's just a free group. So it's matrices. And suppose that that collection of matrices has finite orbit up to conjugacy under the mapping class group. Then we want to show that those matrices generate a finite subgroup generally here. Okay, so I should say I tried to prove this just by hand for a long time. I never got anywhere. In rank 2, there's some beautiful work of Wang, Biswas, and well, I should have written this down, but they managed to find a proof in rank 2 by hand, but still somehow very young. But we really need some algebraic geometry to get started. So let me kind of say what the algebraic geometric starting point is. And for simplicity, I just want to assume that our representation is irreducible. So in the main theorem, well, if rho is semi-simple, you can just take an irreducible component. That will still define an order. So you can say there's a bit of extra work that needs to be done in the non-semi-simple case, and the main idea of the proof is already there if you assume rho is irreducible. And so what's the geometric content here? Well, it's a little observation that if you have a representation of finite orbit, then it almost comes from a local system on CGN, the total space of the universal curve over MGN. So what's the actual statement? This is a little exercise. It's that given one of these rows, there exists a family of curves over some base dominating MGN with 5 monodromy given by rho. So one can just directly construct something. It really uses theories. This object V, it really reflects the properties of rho. So for example, if rho is finite image, then V also.
Given by the kernel of the action.
Yeah, so that would be to start. So that if you take the kernel of the action, you get a finite cover from Gn, and there this rho goes to a projected representation. And why is that? Well, how do you make this representation V given an element of matter cluster? It conjugates your representation to something eccentric, the conjugate matrix. But that matrix is only well defined at the scale. It's only that matrix is only well defined at the scale vector is long. So really you only get something projected, and then you have to pass to a further, not necessarily finite cover to get an honest level. But for the purposes of this, you could actually work with projectiles. So if you'd like, if you want to assume V is projective, you can take M to MGN just to be finite. But we can't quite work with that. Are there any other questions about this? Okay, so this is a geometric situation, and well, motivated by that conjecture I told you before, we want to try to get ourselves into the situation where V itself is some geometry. Okay, so in other words, we'd like to use some Hodge theory. And well, we can't directly apply Hodge theory to V, but what hypotheses would let us do that? So okay, so here's the situation we had before. I'm just copying it off of this slide. We have a family of curves over more or less MGN, some dominant cover from GN, and a local system on them with fiber monodromy we'd like to understand. Okay, well, first we're going to look at the situation where rho itself is unitary. Let me just say what the strategy is. So our goal will be to show two things. Our goal would be to show that this local system V is defined over the ring of integers of a number field. So that's the first thing we want. And the second thing we want is that any way of extending scalars from that number C gives us a unitary local system. So if we prove these two things, we win. Well, why is that? Well, it's because the embedding of the ring of integers in the number field into the product of C, where here this product runs over all embeddings of OK in the C, this has discrete image. Okay, and moreover, the unitary group is compact. So if we can prove these two things, well, what have we shown? We've shown that this local system V, or equivalently the representation rho, has discrete and compact image, and that discrete compact set is finite. Okay, so this is the idea of the strategy, and we're good. So we're somehow going to need to find integrality and unitarity somewhere. Okay, so the first step, I just want to assume my representation is unitary, and we'll reduce to that. So I have a unitary representation now with finite of the conjugacy on the Mapping class group, and I use that to make a unitary local system with family of curves. Okay, and now a unitary local system one can apply the methods of Hodge theory to. And they'll tell us, and I'll say a word about this at the end of the talk. You can compute the deformation space of this local system using Hodge theory. And some period map computation will tell you that this local system V is cohomologically rigid. So what does that mean? It means it's a reduced isolated point of the character variety of C. Where you fix some local monodromies of infinity. In fact, you don't need a fixed local mod. It's even a reduced isolated point of the whole character variety. Okay, so this is the first step. So what does this give us? What does it buy us? So Boton told us that there's beautiful work of A.N.L. Groening, which says that a cohomologically rigid local system, isolated points of the character variety, is automatically defined over the ring of integers of a number. This relies on the course work on the Langland's program over function fields. Okay, so this is the arithmetic input to the argument. Right, so in this unitary case, we've achieved our first goal. We've gotten integrality. Okay, so we're not done. Why is that? Well, we assumed rho is unitary, but we don't know that if you twist it, if you Galois conjugate it, that it's still unitary. So we still need to handle these other embeddings of the ring of integers of K into C. Well, what do we know? We know that this local system V is rigid, which means that, well, under any Galois conjugate, under any embedding into C, it's still rigid. That's an algebraic condition. So non-abelian Hodge theory. So in this case, we need to apply non-abelian Hawkes theory to C, which is a quasi-surjective variety. So it needs the work of Machizuki in addition to Simpson. It tells us that this local system, B tensor C, under this new embedding underlies a complex variation of Hawkes structure. And we would like that complex variation of Hawkes structure not to be very interesting, like it to be unitary. So if you start with something rigid and then you double conjugate it, then it's rigid. But are you asking about the period map computation? So we don't. We start with something unitary and you show it. You have to analyze it. This I can say it's this period map computation. I mean, I'll say something about it, but that's the actual part. Yeah, I mean, I can say something about it maybe at the end of this slide. Okay, so this is just an outline, and I'll tell you where the actual work happens. Okay, so this thing underlies a complex variation of Hawkes structure. Okay, and now let's restrict it to a fiber. So now on every fiber of this family, we have complex variation of Hawkes structure. We want to show that thing is actually unitary. And the observation, I say observation, it's actually very low, is that by changing the fiber in this low rank situation, you can arrange that your vector bundle underlying the complex variation of Hawkes structure is actually semi-stable. And then a curvature computation, which ultimately goes back to Griffiths, tells you that if you have a complex variation with underlying vector bundle semi-stable, then that variation is actually unitary. So the point is that the first non-trivial of the piece of the Hawkes filtration is stabilized. Basically doing some curvature. All right. And okay, so now I've highlighted the hard parts. So the parts that are not just directly applying other people's work are you have to do this period map computation to show rigidity, and then you have to show that you can perturb your fiber of your family if you choose. Both of those are involved. So those boil down to some, I think, not really obvious statements about vector bundles on curves. Maybe let me. So this handles the case where rho has unitary monodromy to start with. Maybe let me show how to reduce to that case, and then if there's time, I'll say something about these hard parts. Yeah, so okay, so we've won in this case. We've proven integral and unitary for all embeddings, and maybe I'll just mention. I mean, there's some interesting history behind the second hard part. So this was a question of Griswold's and Hermes. They asked if you have any flat vector bundle on the curve, can you perturb the complex structure on the curve to make it semi-stable? And there were some claims in the literature that this is always the case, and it turns out that's false. So really needs to do some work. And in fact, that's part of how we got into this. Is we found a counterexample to those claims in the literature. Started trying to understand what was going on. Okay, so now let's just assume that rho is semi-simple. So we don't want to assume unitarity. Okay, well, if rho is semi-simple, I can just take an irreducible constituent. And so I can assume rho is irreducible, but not necessarily semi-simple. And I'll again get this picture where I have a family of curves over some base dominating the moduli space, and a local system on that base, on that family, so that if we restrict to the fiber, you get a representation you share. Okay. And we want to study that situation. Now we don't know anything about V. We don't have any kind of unitarity, well, non-abelian Hawkes theory, so the work of Simpson and Machizuki, tell us that we can deform this local system into a complex variation of Hawkes. So now we have a chance of doing some geometry. So we're going to do that. That could change the monodromy restrict to the fiber in some uncontrolled way. We need to understand that. Well, just like before, we now have a complex variation. Sorry, that V there should be a V prime. We have a complex variation, so we can restrict to a fiber and then perturb the fiber, make the vector bundle semi-stable. So that will tell us that this V prime is unitary. Okay, so this V prime we understand well. It's a total local system on more or less the total space of the universal curve. So V prime is finite over the back question. It's unitary, we've now achieved that. And so V prime is finite monodromy, at least when you restrict to a fiber. Okay, so what does V prime have to do with V? Well, you can now do the same period map computation from before as V prime. And that tells us that V prime is rigid. Okay, there's a little bit of subtlety here on the file. If anyone has questions about it, I can say it for you later. But now we've deformed something to a rigid thing. What does that tell us? It tells us they're the same. So, okay, but it actually tells us, so I'm being vague about what rigidity here, the actual rigidity you get only implies that B restricted to a fiber is the same as B prime restricted. But that's what we need. Okay, so let me summarize that. So we deform to a CVHS, we show that CVHS is unitary, and then we show the deformation is trivial. So now let's reduce to the CVHS case. Or sorry, reduce to the unitary case. Okay, and again, what are the hard, oh, yeah? Yeah, so we really kind of need these kind of explicit form of period map. I mean, you can write down, if you have a CVHS, you can write down the period map. I don't know how to do the computation for CVHS. And I think it would be very useful. People are in this unit zeros unitary is a much strong assumption. But yeah, so I think that's something we're trying to do now with limited success so far. But I can tell you, maybe in the last few minutes, I'll say something about these two hard parts. So this period map implementation, the way we do it really relies on unitarity. So we somehow have to achieve unitarity before we can get rigidity. Okay. And maybe I'll just say a word. So I've handled the semi-simple case. In the non-semi-simple case, you can't take an irreducible constituent, so you somehow need to handle extensions. And this boils down to this Putnam-Wieland conjecture that I alluded to earlier about the monotony of our Persian families. This conjecture is equivalent to Ivan's conjecture that Litt mentioned. So we don't prove that conjecture, but we prove it in large units. And that's what handles the extension. That handles the non-semi-simple case. And I won't say much about it, except maybe that the proof is more or less the same as the period computation that goes into proving rigidity here. Okay. Okay, so let me just briefly summarize the proof. So the first step was to translate the question into an analysis of local systems on moduli spaces. So we started with this pure linear algebra question and translated it to a question about local systems on the universal curves. The next step was to kind of find some secret rigidity. So we started with a local system on a curve that curves with positive genus. It will never be rigid. But we put it in a family, and that's when you put it in a family, you suddenly get rigid. That's somehow the key idea. And then rigidity gave us two things. It gave us an integral, more or less an integral variation of Hopf structure, and then one shows that that variation of Hopf structure is actually unitary. So that's the overview. Okay. Let me just finish up with some final questions, and then if people are interested, I can say something about hard parts of the proof. So for me, the following two hard question is like very, it's like, I think this question is very inspirational. Which local systems are unit? So smooth plus projective variety, you can ask which representations of the fundamental group show up in the monodromy homology of the family frame. So this question is too hard. Even if you ask it for curves, why is that? Well, if you ask it for curves, the answer depends on the complex structure. So if you want to have a chance of answering the question, you need something kind of purely topological. So here's the revised question. It's interesting. Can you classify the local systems on a topological surface, which are of geometric origin for all complex structures on that complex? So that's the most naive thing you can do to make a question about complex geometry into a question about topology. Just make it independent of the complex structure. Okay, so this is the key addition. And the sort of trivial observation is that if you have such a local system, it automatically is time. So you can ask which. So in other words, this classification becomes which representations with finite orbit under the mapping class group come from geometry. Okay, and then the super rigidity question from before predicts that all local systems on sigma gen of this property are actually of geometric origin. So in other words, this property of being of geometric origin for all complex structures on a surface should be equivalent to this for irreducible local system to having final. Okay. Yeah. So those are my final questions. Maybe I should not say anything about those hard parts unless people have questions about them. So let me end here.